Hello everyone. In this video, we're going to write Verilog to implement a single neuron in hardware. We're starting here because if you know how to implement a neuron on an FPGA, then you will know 60% of what is needed to build an entire feed-forward neural network. As a reminder, the end goal of this series is to build a simple feed-forward neural network with 3 layers and 60 neurons. We're going to write the Verilog code for the entire network, and then we're going to deploy it on an FPGA and do real-time image classification. Images will be sent from a computer to the FPGA over UART. The FPGA will run inference on the network and output the classification result in real time. And this is a pretty serious build. This project alone was enough to count as a master's thesis, so we're going to take it step by step, which is why we will start by building a neuron. Alright, so let's get started. As a quick review from the last video, a neuron is a simple mathematical operation. It takes in an input vector x, a weight vector w, and a scalar bias b. Then it computes the dot product of x and w and adds the bias. So the output is x dotted with w plus b. That's the exact calculation that we're going to implement in Verilog. The entire video will revolve around designing circuitry to take the dot product of two vectors and then add a constant. When you're building hardware to do a math operation, you first have to decide where are you going to store the inputs. For a neuron, we have 3 inputs, the vector x, the vector w, and the bias b. The input vector x changes each time we run the system, so we store x in RAM. But the weights vector w and the bias b don't change during normal operation. Once the neuron is trained, those values are basically fixed constants, so we can preload them into a ROM. So the main idea is simple. X is the only thing that changes, W and B stay the same. Because X changes, we use RAM or random access memory. Because B and W never change, we use a ROM or read-only memory. So how are the inputs actually stored in these memories? Well, it's actually pretty straightforward. For both vectors, we store them in order, 1 value per address. Element 0 goes at address 0, element 1 goes at address 1, and that just continues all the way up until the last element in the vector. We do the same thing for the weights ROM. W0 at address 0, W1 at address 1, and so on. For the bias, we're only storing 1 value, so we just put B0 at address 0 in the bias ROM. And yeah, technically we could store the bias B0 in a single register, but it's better using this architecture because it will save time when we move on from one neuron to many neurons. So this circuitry here is what actually computes the dot product and then adds the bias. The way it works is we go through the 2 vectors one index at a time, and each time we select one entry from the XRAM and the matching entry from the WROM, we multiply them and add that product into a running total stored in the accumulation register. By pulsing P1, we set the address we want to read from XRAM and WROM. By pulsing P2, we read the X value and its corresponding W value, and then by pulsing P3, we accumulate the product into the running sum. We repeat that 3-pulse sequence over and over again until we've processed every element in the vectors, and at that point, the accumulator holds the dot product. Finally, we can handle the bias. Pulsing P4 selects the bias location, and in our case, that's always address 0. Then pulsing P5 reads the bias value, so we can add it to the accumulated dot product and produce the final neuron output. After P5 is pulsed, the calculation is complete. Now let's walk through how the circuit works. This part of the circuit calculates the dot product between the W and X vectors. To run it, we repeat a simple 3-pulse sequence. P1, then P2, then P3. We keep repeating this until we finish the dot product. To make this easy to follow, I'm going to show you an animation of how it works. We start by pulsing P1, which sets both address generators to address 0. Next, we pulse P2, which makes the XRAM and WROM output the values stored at address 0. Once those 2 values appear, the multiplier produces their product, and the adder adds that product to the current accumulator value. At the beginning, the accumulator register starts at 0, so the sum is just the product. Then we pulse P3, that stores the adder's result into the accumulation register. After that, we repeat the exact same 3 steps for the next pair of values. We pulse P1 to move to the next address. We pulse P2 to read the next X and W values. and we pulse P3 to store the updated running total. After we repeat this for every element in the vectors, the accumulator register holds the full dot product. Once the dot product is stored in the accumulation register, we move on to the bias. The portion of the circuitry that is driven by P4 and P5 is what adds the bias. We pulse P4 to select the bias address. In our case, it always points to address 0. Then we pulse P5, which makes the bias ROM output the bias value stored in address 0. At that point, the adder combines the stored dot product with the bias, and that gives us the final Neuron output. So let's summarize how this Neuron calculator runs from start to finish. You pulse the reset input once to reset the address generators and the accumulation register to their initial states. Then to calculate the dot product, you pulse P1, P2, and P3 in a burst n times, where n is the number of elements in x and w vectors. Finally, to add the bias, you pulse P4 and P5 once. After pulsing P5, the Neuron output is complete, and the waveform below shows the general process used. Now before I show the final Verilog code, let's briefly discuss the Verilog code for the lower level modules. These modules are not that complicated, but they are worth reviewing. So the XRAM is just a simple memory unit as shown here. The WROM2 is a simple memory unit, and the same thing for the BROM. It's important to note that all three memory units take in parameters to control the widths of the data, the widths of the addresses, and the initial contents. The address generator for X is a simple counter that continuously increments its output after initially outputting 0. The address generator W is the exact same thing, though it's best to give it its own module to make our circuit match the format of a real accelerator. The address generator for B is kind of funny since it takes in a pulse and always outputs 0. We could technically avoid this by hardwiring the adder to always add the bias, but that would be bad because then we won't be able to reuse the architecture later on when we modify it to evaluate a full layer. Then we have our combinational adder and multiplier. The code for the multiplier can be complex depending on how we want to multiply it, but the behavioral description for it works perfectly fine as a proof of concept. Then lastly, the register bus can be made using the simple code shown here. Alright, so now that we've gone over all of the lower level modules, let's go into Vivado and view the top level module code and see it simulating. So this here is the top level module. The top level module just interconnects the lower level modules to implement the complete circuit we already discussed. And again, the lower level modules we discussed are all shown below. So just to prove that this works, let's go through a test. In our test, we will have these values stored in memory. On the right is the true value, and on the left is the hexadecimal equivalent stored in the mem files. For this test, I chose to use signed 32-bit values with 16 bits of fraction. When we run the simulation, we can see the contents in memory being shifted out in real time after each P2 pulse. We can also see the accumulator adding them after each P3 pulse. Then, after 5 iterations have happened, we pulse P4 and P5 to add the bias, and we can see that it works, and then we get out the final result. So this is how you design the circuitry to compute the result of a neuron. In the next video, I will explain how we can reuse this exact architecture to process many neurons at a time. That's all for now, and looking forward to seeing you next time.